So let's talk about lens error. So remember I talked about a fisheye lens, that 14 degree. So if we had a 14-degree lens, 14 millimeter focal point lens in our camera, this is the image we'd probably get. This is called a fisheye. That simulator didn't show us this distortion because that wasn't the point of that simulation. But this is in fact, with a lens that short, you'd get this kind of what's called barrel distortion. This is an exaggerated thing. So there's two things I want to separate. One is a fisheye lens does this on purpose. And the reason it's called a fisheye lens is that this image is imagined to be what a fish would see if a fish eye could be seen through, right? And also because fish eyes tend to bulge. But anyway, but more importantly, there's much more subtle distortion on poorer quality lenses, or especially on poor, or when you go super wide on a zoom lens, you'll get some of this barrel distortion, right? Some of you guys that have got GoPros will know that Premiere and Photoshop and a few other programs have filters or have adjustments that will automatically compensate and readjust the image physically to get rid of this distortion. It's caused because the angle is too wide. And sometimes you get to the point where it's so wide, it's unavoidable. Once you start getting into like 155 degree, you'll start to see the images just curve naturally, right? And you can see this is a building. If you think of this as like an alleyway or a walkway down between two buildings, at 155 degrees wide, it looks quite distorted because it is. You're seeing it unnaturally, right? So that's barrel distortion. The important point here is we're going to buy a camera lens, take a chart like this with you, except this chart has been distorted to show the barrel distortion. You can download the chart as perfectly normal squares, shoot it with a camera lens, look for barrel distortion, zoom in and out, especially if you're buying zoom lenses. You know, see if they have a distortion chart in the shop, and if they don't, bring your own and zoom in and out and see if these lines start to stretch and warp. If they do, the lens isn't as good quality as it should be. Our eyes do it too, but the brain fixes it, right? Our eyes, because they're a little bit wide-ish, but our brain fixes that distortion. Otherwise, if the world was all distorted, we would have issues getting around. Okay, the other one is called pincushion, and this is more common on zoom lenses when you're zoomed all the way out to maximum magnification, or telephoto lenses, long telephoto lenses. Most consumer zoom lenses have some pincushion distortion, but high-quality cinema lenses do not. And again, if you look at it on a chart, it'll look like this. So now all the lines are squeezed towards the center. Again, I'm not sure why it's called pincushion, but maybe because it looks like a pincushion, I don't know. Another error you can get in lenses, something called spherical aberration. And what spherical aberration is the tendency of the light rays to bend at different angles because of the shape of the curve of the lens, right? And so what that means is you end up with multiple focal points. It's not the same as a circle of confusion where we got a focal area. It is kind of like that, but it's actually worse because the focal points are all stacked up on each other along a line, right? Because the light rays are bending at different rates along the surface of the lens. A perfect lens without aberration will be engineered so that the curve is such that the light rays all bend at the same rate, or are bending at the rate to make them all meet at one point, right? So you get a much sharper image. If we look at light going through a lens with spherical aberrations, you do get a bigger circle of confusion. It's a weird shape. So the one in the center is not, it does not illustrate the aberration. The ones on the top and bottom do. You can see, if we're looking at the light sideways, we're not looking at the light on the focal point, we're looking through the light beam at the focal point. You can see this is quite tight and this is all loose. And you can actually see the individual rays stacking up, right? So that's spherical aberration. Again, it's fixed by having an aspherical lens element. That's another way to do it. It's the way high quality lenses do it. They'll have one element inside and its whole job is designed to converge all this light and get a sharper image. Costs more money, okay? So keep that in mind. And then the other one's called chromatic aberration. And chromatic aberration is the nature of physics. When light of different frequencies hits a refractive index, it bends because the frequency is a different wavelength, which means it's a different speed, right? And as a result, it bends at a different rate, traveling through the material, very slightly different rate. And so you get what's called chromatic aberration. And again, this can be rectified. If it's not rectified, you get what's called fringing. And fringing is this weird color glow, sometimes blue, sometimes red, depending on the frequency that's being affected, sometimes multiple colors, like a rainbow effect, on the edge of high contrast. So white, in this case, white leaf to dark shadow. On the edge of that, you're getting the blue fringing. You fix it by putting another element inside the lens, right? And that's called an achromatic doublet. And what that does, don't worry about that name, but what that does is it bends the frequencies together, it compensates for the frequency change, and puts all the light back at a single focal point. So again, it's an additional piece of glass inside your lens. Cheaper lenses don't have these kinds of elements in them and are therefore more subject to chromatic aberration, okay? Lens flare. Lens flare is not really a quality issue, although there can be issues with the coating on lenses, but lens flare is caused by, and I'll just show you here. You can see the number of rings. So each one of those rings is a glass refraction inside the lens barrel. So we have what, 1, 2, 3, 4, 5, 6, and then this dot is probably 7. There's probably 7 elements inside this lens, right? Along with the coating that's reflecting all these little dots. These are after effects of the flare. This is the flare here. And what the flare is light comes in from the lens at an angle and then refracts when it changes index from leaving the lens. And the refraction is, the angle is such that it refracts right back inside the lens. It becomes what's called an internal reflection. And that reflection then moves further down into the image, right, off the line of the original light ray, and then ends up coming back, bounces back out, and then goes somewhere unwanted, okay? So that's lens flare. So the big way to get rid of lens flare is if you have a lens hood. I'm gonna go back to this diagram because it's bigger. If you put a lens hood out long enough to intercept that light ray, so if of course I can't show you because I can't show you with my hands. This is crazy. If you have to imagine that I'm drawing a line along where the cursor is, as soon as that line crosses that light ray is broken and can't get into the lens. So this is why it's important to use lens hoods outside or matte boxes outside, because that deep well that the lens is in prevents all this light from coming in off the side, okay? Okay, and then the next thing to talk about, one of the last things to talk about is coatings. So this picture is of consumer eyeglass lenses. I do not expect you to remember any of these coatings at all because they're different. For every manufacturer has a different formulation of coatings, what they call them, what they do. But the important issues are that you've got a coating to prevent reflection. In this case, they call it the advanced light control coat. You've got a hydrophobic, for glasses you'll have this. You won't have this so much on camera lenses. The hydrophobic coating is one that sheds water, so you don't get fogging and steaming. Not so much a big deal with camera lenses as it is with, because there isn't a nose in front of a camera lens blowing all this moist air out. Then you have hardened coatings, which are harder than the glass and the lens, right? So it's a coating, all these coatings are put down on top. They're not brushed on. They're usually put down using what's called evaporative techniques, where they evaporate the material in a vacuum or a special chamber, and it settles on the glass. They're all very, very thin, sometimes only a couple of molecules thin. So they do a number of jobs. Like I said, they prevent reflection, they prevent glare, they'll prevent a little bit of lens flare, they'll be harder than the glass. The point of all of this, other than knowing that they're there, that they're good quality things, is don't touch the lens. If you touch the lens with anything, including a lens cloth, these coatings can be damaged. And I see it all the time. People grab a lens paper, there's special papers, and oh, it's lens paper, I'll just use that. The problem with lens paper is the paper fibers can be sharp. Lens paper has to be used flat. You don't ball it up and wad it up like a Kleenex and rub it. You have to rub them flat. So I prefer people use lens cloth. Make sure the cloth is clean. So if you use lens cloth repeatedly, make sure you wash it every so often. Try not to wash it with too much detergent. Use a bit of dish soap if you need to. But you've got to make sure you don't scratch these things because they're very hard to fix.